Morning, everyone. Good afternoon. Welcome to all, and thank you for joining us today for MIT InnoTherm Colloquium number 10. The InnoTherm Colloquia are organized by the Department of Mechanical Engineering at the Massachusetts Institute of Technology, and they cover biweekly topics at the leading edge of thermal science and engineering. Today, we are pleased to have a panel that will discuss thermal engineering challenges around electric vehicles. We will hear about the general architecture of these vehicles. We will hear about how heat pumps and refrigerants affect the performance and range, how the outside climate affects the performance of the vehicles, and the broad spectrum of trade-offs that vehicle manufacturers confront as they optimize around these variables. Our panel today will be moderated by Aiden Abubaki from Tesla. Aiden is a principal thermal engineer at Tesla, where he works on electronic cooling systems in EVs, thermal management of the autopilot, and thermal modeling of electronic systems across the entire car. With that, Aiden, the floor is yours.
Thank you, Professor Leinhardt. My name is Aiden Abubaki from Tesla. I'm very happy to be moderator for this webinar today. Good morning, good afternoon, good evenings to people who have joined us. Thank you for joining. It's going to be an exciting line of presentations today. We will start the presentations with the presentation from Christine Almon, mostly covering the architecture of EVs and most back-to-back discussions after that. Professor Almon is currently a professor of mechanical engineering at the University of Toronto and alumni distinguished professor in bioengineering. She was formerly Dean of Faculty of Science and Applied Engineering, and before that, and Lane Distinguished Professor of Mechanical Engineering at CMU, at the same time Director of Institute for Complex Engineered Systems there. She has won many numerous awards, including Canadian Academy of Engineering, Hispanic Engineering Hall of Fame, National Academy of Engineering, Royal Academy of Spain, and Royal Society of Canada. Her selected list of her research areas include nanoscale thermal transport, energy systems, thermal management of electronic vehicles, hemodynamics, and transport in biomedical systems. Our second speaker, Professor Jürgen Kohler from University of Braunschweig. He was formerly a consultant engineer and was lead author of RTOC chapter working group for United Nations Environmental Protection team. He has won awards, including German Environmental Award in 2007 from German Environmental Foundation, DVU. And his research areas include energy conversion, transport and storage, alternative refrigeration and heat pumps technologies, heat and mass transfer at both material and devices, fuel cells, and thermoelectric materials. Our third speaker will be Professor Stefan Elbel from University of Illinois at Urbana-Champaign. He is Associate Director of Air Conditioning and Refrigeration Center and Chief Engineer at Creative Thermal Solutions. He's an active member of many professional societies, including ASME, ASHRAE, SAE, IIR, and IIAR. His research interests include fundamental research in thermodynamics, fluid mechanics, and heat transfer, and components and systems in mobile, residential, commercial, industrial heating and cooling applications. Energy conversion with a specialization in sustainable vapor compression technologies is among his research areas. And we will conclude today's presentation with an overview of industry trends and presentation from Mr. Jürgen Gertenbach. He is a retired senior engineer in mechanical engineering, working previously at Daimler in Germany. And he's coming with many years of experience, and his expertise include thermal management of electric vehicles, HVAC of passenger cars, natural and HFC refrigerants for automotive industry, and safety assessment of AC systems. Before starting the presentation, I would like to share a few housekeeping items. As mentioned, we will have about 4 presentations, 10 minutes each, and we will follow up with discussions and some closing remarks at the end. We would love to hear your questions. Please submit your question through the Q&A button at the bottom of the page. You will see there. questions will be visible to the panelists and other attendees. If you wish to prefer anonymous, please mention that in your question and we will post that question as an anonymous question. We would also love to hear about your suggestions you have for future topics, speakers, and format of these presentations. Please also note that this webinar will be recorded and will be later on posted on YouTube. This may also include questions which we cannot get today. With that, I would like to start the webinar by sharing a poll. So that would be a good opening remarks. So our poll number 1, let me launch the poll. It's a question about number of EVs. In 2010, we had about estimated 17,000 EVs on the world roads. In 2020, it's estimated to be 7.2 million. In 2030, is expected about 140 million. The question is, what fraction of the global vehicle stock is expected to be EVs in 2030? I can see that answers are already trickling in. Let's give it a few minutes. Thank you for participating. You can access the poll option at the bottom of the screen. Okay, the question is, what fraction of the global vehicle stock in 2030 will be electric vehicles? And this will not include 2 or 3 tricycles. Okay, seems that we're getting to steady. So let me share the poll results. 3% of participants, just changing. 6% of participants think that it's going to be about 3% of global fleet. 15% of participants believe it's going to be about 7%. 44% of participants chose 15% of global fleet, and 35% think it's going to be about 30% of global fleet by year 2030. You will hear more about this in Professor Christine Almon's presentation. So with that, Professor Almon, I'll pass the mic to you.
Can you share screen or stop sharing screen?
I should stop sharing. You should be able to share at this point. We can see your presentation.
You can see now. Okay,
yeah.
Let me get to the start. And let me say that the answer to the poll is 7%. So 7% of the global car stock is expected to be electric vehicle in year 2030. Currently, there are over 7 million electric vehicles on the road, up to from 17,000 EVs just a decade ago in 2010. By 2030, based on a recent report of the International Energy Agency, we expect to have between 140 and 245 million EVs out of a total of 2,000 million cars. Now, the lower end, 140 million, 7%, represents the estimate that assumes that the existing government policies remain as they are today. In the upper end of 245 million is around 12% EVs, which assumes more aggressive incentives and policies so we can start meeting the environmental goals of the Sustainable Development Scenario. The cost of batteries for EVs has been falling rapidly, driven in part by the introduction of new cell chemistries, cheaper manufacturing, and simplified battery pack designs. For instance, the current cost of battery packs is, in average, $156 per kilowatt hour, down from $1,100 in 2010. And by year 2030, the battery cost is expected to reach around $61 per kilowatt hour, which requires high levels of investment to keep prices falling. I want to note that this cost includes also the battery packaging and the thermal management system in addition to the cell cost. Therefore, the cost of EVs has been decreasing, and together with government incentives, EVs are becoming competitive, comparable with internal combustion engine cars. However, the driving range anxiety remains the big issue impacting mass adoption of EVs. How to address this range anxiety? There are two basic approaches. So it seems you cannot see the video.
We see your slides, not you.
Oh, I see. Okay. Let me continue and then try to work on that. So the driving anxiety, as we were saying, how we could address that. So there are two basic approaches. The first one involves increasing the battery capacity, which results in larger size, weight, and cost of EVs. And the second approach is to enhance significantly the fast charging and its public infrastructure, which will enable users to recharge the EV quicker and more frequently. Will be similar to refueling in conventional gasoline stations, that is to charge roughly 200-kilometer range in 5 to 10 minutes or so. Extreme fast charging, XFC, will allow this, but requires over 350 kilowatts power, and most importantly, requires tremendous heat removal rates of the order of 25 kilowatts or more. There are other thermal challenges and opportunities to improve EV performance and its corresponding driving range, such as to keep the battery at optimal temperature, which for lithium-ion battery is between 15 and 35 degrees approximately, both for performance and degradation. This would require heating and cooling at extreme ambient temperatures particularly. Another thermal challenge is to keep uniform the temperature within the cells and across the thousands of cells in battery packs, which are connected in series and parallel. And this requires effective cooling at the packet level, at the battery level, at the module, and at the cell. Another issue is to mitigate battery degradation and aging, which also will help maximizing driving range and lifetime of the battery. All these related to temperature issues. And other thermal issues are related to safety, the risk of runaway and fire, as we discussed in a prior InnoTherm colloquium. All this requires technological, thermal innovation, and intelligent thermal management systems for EVs. The EV thermal management system provides the cooling and heating to the battery, to the cabin, and to the electrical motor inverter and their power electronics, all under dramatically different temperature conditions and requirements. Therefore, an EV thermal management system usually has three main circuits or loops And here is a representative scheme of them. The blue circuit performs the critical cooling heating of the battery and keeps the cell temperature in the narrow range for optimal operation. And this is the low temperature circuit. Typically uses water glycol cooling, where the temperatures are significantly lower than in conventional internal combustion engines vehicles, with the corresponding heat transfer challenges. And the heating also may require a preconditioning in cold weathers, and we'll hear more about this and a lot about preconditioning from Stefan Elbel's presentation. The red circuit is to cool the motor and inverter, which has power electronics with a maximum temperature operating junction temperatures on the order of 100 to 150 degrees centigrade. Typically, again, water glycol is the working fluid these days. And the yellow circuit is the vapor compression refrigeration cycle for the cabin thermal comfort and the chiller. Can also operate as a heat pump, and it can have different refrigerants from synthetic fluorocarbon to CO2. And Jürgen Kohler will describe the effect of different refrigerants and more. And the circuits can be combined in an effective way in a variety of architectures for different applications. And Jürgen Winterbach will provide insight into this. And going back quickly to other challenges and requirements for increased cooling, we need advanced battery cooling strategies to enable extreme fast charging, particularly on the road, to make charging times in EVs comparable to refueling times in conventional vehicles. And this requires that the thermal management system for charging will have to increase from today's size of 1.1 to 5 kilowatts to over 25 kilowatts. And to meet this battery cooling demand during extreme fast charging requires either to increase the onboard thermal system capacity significantly, and to supply independent cooling by the charging stations. One option would be to provide chilled water or coolant from the charging station to the EV. But however, integrating both cooling systems from onboard the EV and from the charging station is a challenge which requires coordinated solutions. And the question is, who owns the solution of the cooling strategy? The car manufacturer, who designs the onboard cooling system and is typically independent from the charging stations, or is it owned by the charging station? Thermal management of batteries, keeping their temperature within the optimal range, is crucial to improve battery performance, which also affects the driving range, to reduce degradation and maximize lifetime of the battery, and for safety considerations, as thermal failure occurs at both ends of the temperature. For instance, at low temperatures and fast charging, we have lithium plating and cracking that occurs, and at high temperatures, there is growth of the solid electrolyte interface, and this can induce thermal runaway, fire, and explosions. Another requirement for thermal management systems is to keep the temperature uniform within the cell and across the thousands of cells in the battery pack as they are connected in series and parallel to avoid developing different degradation paths. In addition, advanced temperature sensing techniques can deliver real-time thermal data for active cooling. So this requires either embedded sensors in battery cells or fiber optic sensors to monitor the cooling effectiveness and the hotspot, and can provide warning well in advance of potential failure. Other opportunities to recover waste heat, to utilize heat pumps, and the importance of hierarchical modeling will be presented in this webinar as well. Very quickly, I'd like to share with you the battery pack cooling design and integration done by my team. As the electrical vehicles is a complex system, improvement of one parameter might affect negatively the metric of other components of the electrical vehicle. Therefore, we need a holistic approach. And at the University of Toronto, we're instrumenting a concept EV. This is the yellow car in this figure. And we're assembling the full battery packs through multidisciplinary collaborations and in collaboration also with industry, so we can deploy this technology operating under realistic conditions. And this deployment is essential because of the interconnectivity of the different scales and subsystems in the EV, which is also crucial for the calibration, the validation, and optimization of the multi-scale thermo-electrochemical models from the cell to the vehicle. We have designed and optimized then manufacture and assemble a multifunctional and scalable battery module. Within this integrated approach towards battery and EV thermal management, so we're tackling the thermal challenges at different levels. For instance, through temperature uniformity, which has tremendous impact on fast charging, and also by enabling a seamless transition of the modular design from EVs to second life stationary applications. This impacts the value proposition for batteries and EVs if we can reuse the batteries for second usage, second life after they are disposed from the EVs. The battery packaging design has a double function for mechanical support and also for cooling, reducing the contact resistance. The parallel cooling approach of the module yields superior heating cooling performance because it minimizes the temperature gradients across the battery cell and also provides rapid cooling necessary for fast charging. A few additional comments. The parallel arrangement of extruded channels allows for the distribution of the coolant with a minimal pressure drop across the channels. And the heat exchanger also can be made in a light material, which may account only for 10% of the total battery module weight. And as the last topic of my presentation, I would like to mention the importance of hierarchical modeling, multi-scale, and multi-physics modeling. Advances in EV technology require knowledge of the thermo-electrochemical phenomena, which is highly coupled across multiple scales to address all the interconnected challenges from a holistic perspective. In understanding and modeling heat generation and the effect of temperature in battery systems requires to start within the individual cells to the interconnects between the cells across the entire battery for designing effective thermal management systems and for integration and optimization. So the thermal properties of batteries are as important as the electrochemical properties. However, temperature-induced phenomena are typically disregarded at the nanoscale model of the batteries without accounting for the electrodes' thermal capabilities to dissipate heat. For instance, the electrodes at the atomistic level simulation, their thermal conductivities depend on the battery state of charge, which can be only evaluated at the battery pack level. So very quickly at the electrode level, atomistic simulation with molecular dynamics, first principles, and machine learning enables the evaluation of thermal conductivity, intercalation energy, and so on. And it is also at the electrode and cell levels that thermally related failures occur, which underscores its relevance. So the hierarchical modeling approach spans across 7 orders of magnitude of scales, starting from thermophenomenon at the electrodes with atomistic models, then to the cell and to the module via thermal and fluid flow CFD, and all the way to the battery pack in the EV circuit with reduced order models. And similarly, for the thermoelectric co-design of inverters and their power electronics, we need to consider all relevant scales from atomistic level to the transistor and magnetics to the inverter and onboard charger in order to perform system integration and optimization. This is the end of my presentation, and I'll pass now share screen to our moderator, Aiden Abubaki, for the second poll question.
Thank you very much, Professor Ramon, for a very nice presentation. It gave a very good overview from all the thermal challenges that we are facing in EVs. Before we continue with the second speaker, I would like to launch a second poll. Our second poll, you should be seeing on screen, is discussing the performance drop in EVs at cold climate. The question is, what is the typical percentual driving range reduction of a battery-driven electric vehicle due to lower temperature of the cells and cell resistance heating of the passenger compartment at -20 C or -4 degree Fahrenheit ambient temperature? So, let's repeat the question. How much percentual driving range reduction do we expect at -20 Celsius or -4 Fahrenheit ambient compared to normal 10-20 degrees C ambient? You can see answers are trickling in. So give it a few more seconds so we have input from all the attendees. Thank you all for participating. So you can see numbers are barely moving. So just to share the answers, 10% of participants think it's going to be 0 to 20% drop in the performance or driving range. 57 of participants think it's about 20 to 40%. 31% believe it's going to be 40 to 60% drop in the driving range, and 3% think it is going to be between 60 to 80%. So with that, I'm going to hear more about effect of temperature on EV's range and how we are tackling that in Professor Jürgen Coulter's presentation. Professor Kohler, I'll pass the mic to you.
Thank you. Hopefully you can see.
Yeah, we can see your presentation.
All right. So first of all, I would like to say thank you. It's an honor for me to be part of this great panel here. And I am going to talk about the component in the battery-driven electric vehicle which uses the most of parasitic energy, the heating, ventilating, and air conditioning system. Yes, here you can see the range, the driving range without any HVAC. You have maybe 100%. It's AC on, you have a certain reduction, and heating at very low temperatures, you might end up with a reduction of 50%. So that is basically the answer of our poll. Between 40 and 60% is possible at very low temperatures. However, only if you use an electric resistance heater where all the energy for the passenger compartment heating comes from the battery. However, we have better ways to do that, since the second law of thermodynamics permits that a part of this thermal energy for passenger compartment heating comes from the environment. Only 1/3, more or less, we have to provide by electric energy from the battery, and 2/3 can come from the environment, even if the environment is at very low temperature. And it's even better, this so-called heat pump, this system here, is already on board in form of the air conditioning system here. Usually, even electric vehicles have air conditioning. As it turns out, this is basically the same process, the air conditioning and the heat pump process. We only have to switch the car from the hot end to the low end, and of course the environment also we have to switch. Here you see a pressure enthalpy diagram, the pressure and the enthalpy here, and you can see the 4 changes of state of a typical vapor, compression, refrigeration cycle or heat pump cycle. We have these 4 changes of state from 1 to 2, a compression from low pressure, low temperature to high pressure and high temperature, a heat release from 2 to 3, either to the passenger compartment to heat it or to the environment. Then a throttling process, an expansion process from high pressure and temperature to low pressure, low temperature. And here the temperature is so low, it's below the ambient temperature, so that we, even in wintertime, we can add heat from the environment to our system. That's the location where we gain thermal energy from the environment. And then this 4-1 process closes the cycle. Of course, for the cooling mode, this is the state, change of state, where we cool the passenger cabin. So I should mention one thing here which is important. They both cycles, both modes look pretty much the same. However, there's one difference. The pressure at the low pressure side for the heating mode is much lower than for the cooling mode. This has effects on the efficiency and on the capacity, and even might cause some challenges if this pressure goes below 1, which means below the atmospheric pressure. But I will get back to that later on. Now I'd like to discuss a little bit how such a reversible heat pump, which is able to heat and to cool, is hooked up. As we can see here, I will start with the cooling cycle, the air conditioning cycle. Here's the compressor, compresses the refrigerant to high pressure, high temperature, goes through valve 1. We have 4 valves here, 2 are open, valve 1, valve 3, and 2 are closed, valve 2 and valve 4. The heat at hot temperature level is released to the environment, then it is expanded to low pressure and low temperature, lower than the temperature of the passenger compartment, so we can cool the passenger compartment in the cooling mode, and then it goes back to the compressor. Now we close valve 1 and valve 3, and we open valve 2 and valve 4, and now the refrigerant is compressed to high pressure and high temperature and goes to the indoor heat exchanger, heating the passenger compartment. Then it is expanded to low pressure and low temperature, picking up heat from the environment. Here the temperature is lower than the temperature of the environment, and through valve 4 it closes the cycle. We also need a receiver to store refrigerant, because the amount of refrigerant in the cycle is different in the heating and the cooling mode. So this brings me to the choice of the refrigerant, which is really a challenge. We have a huge variety of refrigerants to choose from. However, as it is always the case, if you have a lot of options, you do not really have a good option. We have synthetically produced refrigerants and natural refrigerants. Here are a selection is provided. Synthetically and natural refrigerants might be pure substances or mixtures. And here for the synthetically produced refrigerants, of course, because they are produced in a huge amount of a quantity, and finally will end up in the atmosphere, we have to pay attention if there are any harmful effects on the environment, as we had with the first refrigerant, this R12, which destroyed our protective ozone layer. Then came 134A as a replacement, but 134A still has such a high global warming potential that it is banned in Europe for car air conditioning applications. And the replacement, the alternative for this is now R1234YF, which is a good refrigerant for air conditioning. However, it might have some disadvantages for the heat pump mode, because the pressure is relatively low. So, and on the natural refrigerant side, we have CO2 as a refrigerant, propane or mixtures of propane, butane. There are also other options like air, water, ammonia, but all these refrigerants here, they have some positive aspects, but also some drawbacks. So as an example, I would like to evaluate these 7 refrigerants here in this matrix. And we can cancel out here. I have 3 parameters or evaluation criteria: operation pressure, flammability, and global warming potential. And we will sort out the very flammable refrigerants and those with relatively high global warming potential. So, and we will just continue on with 1234YF, the mixture 445A, and the CO2, the natural refrigerant, which has a relatively high operating pressure, which is a challenge, of course, because to avoid leakage. However, it will turn out that for the heat pump at very low temperatures, it might be an advantage. 1234YF is the refrigerant which is used today in worldwide in all car air conditioning systems. Also, some heat pumps already have this refrigerant, and I will now investigate or discuss the efficiency, energy efficiency of these refrigerants here. And I will use also data for 134A because these two refrigerants are very similar. Their thermophysical properties are very similar. So I can use the data of 134A in order to evaluate 1234YF. So efficiency, I will focus on the passenger compartment without the battery, possible battery heating and cooling. I already discussed the hookup without the battery because it's just for the sake of clarity. I will concentrate on the passenger compartment heating because it's a major part here, and I will use the number, so which is called coefficient of performance, which is the ratio of the heat, the thermal energy for heating the compartment, divided by the energy power input from the battery. And I will investigate these three refrigerants. Here you can see the COP at three different ambient temperatures, minus 20 degrees Celsius, minus 10 and 0. And I know these numbers are debatable because they depend strongly on the operating conditions, on the boundary conditions, and depending on these conditions, you get different numbers. And I try to find comparable data in papers where at least the authors compared two of them, either these two or these two, to get a realistic relation for these numbers here, even though I know it's debatable. However, what you can see at very low temperatures, minus 20, the 1234YF and all the mixture here, they are not really well suited for the heat pump mode. They just have a COP of 1, meaning the energy which goes into the system goes also out of the system, but nothing is gained from the environment, as is the case for the electric resistance heater here. CO2 with a high pressure, operating pressure, has an advantage here, and here we can really gain something from the environment, and we reach a COP between 1.5 and 2, more or less. However, the days where it's so cold are rare. Even in Boston or Chicago, you rarely have days below minus 20 degrees C. Much more often you have days around 0, between 0 and 10. As a matter of fact, is the temperature range where most of the driving occurs. And as you can see here, the COP difference is not so significant anymore. And this can also be seen in the driving range. And as the COPs are debatable, the ranges, the driving ranges are even more debatable, because here not only the performance, the COP of the heat pump determines the range, but also other parameters of the car, like the cell temperatures and the capacity reduction of the battery at low ambient temperatures here. That's why I included also this black arrow, which is the range at 10 degrees Celsius, at 0, minus 10 and 20 degrees. And you can see it goes down due to the battery capacity, which decreases. And but it's not a surprise that the range reduction looks a little bit better for CO2 at very low temperatures. However, the difference in ranges is almost negligible at 0 degrees, and even at higher temperatures we see almost the same ranges for the different refrigerants. So that brings me to the overall picture. If we look at the a virtual fleet consumption, if all the cars on the whole world were electric cars and used either resistance heaters or heat pumps, then you would see that the electric energy consumption is significantly lower for the heat pump than the electric resistance heater. So this is the energy used for air conditioning and heating averaged over 1 year over the whole world for different regions. North America, Europe, and Asia are the 3 major markets. And these are the worldwide numbers here. But you can see the difference between the different refrigerants is negligibly small, because most of the driving occurs at temperatures between 0 and 10 degrees, more or less, where the COPs are almost identical. So this brings me to the conclusions. Thermal management in battery-driven electric vehicles is very important, because the heating, especially the heating, but also the cooling, can reduce the driving range significantly. And you have to pay for this energy. It's not free, like in combustion engine cars, internal combustion engine cars. You really have to pay for this energy. The efficiency of heat pumps is better than that of electrical heaters. It's also important, because you have to pay for the additional electric energy for heating or cooling the car. The choice of refrigerant does not really matter for the annual efficiency of the HVAC system. However, at very low temperatures, the choice might matter, because you might get a better range for particular refrigerants for the few days where it is very cold. Thank you very much. Now, that concludes my presentation. Now I'm handing over to Stefan Elbel or to Aiden. How do I do this?
All right.
All right.
If you could please stop sharing, and I will share my screen.
I try to do this, however. It
should be at the top of the page if you hover your mouse.
Top of the page. Okay, I was looking on the top. All right.
Let's see.
Now?
Okay.
Right.
Yep. We can see Stefan's. Yeah. Thank you.
Fine.
Let's put full screen here, and then we can get started. So hello, everybody. I'm Stefan Elbel, and I will talk about the topic of preconditioning. And so the first question is, what really is preconditioning? And in short, that is really preparing an electric vehicle either for charging or in general for a future trip. So that means in summer, I want to pre-cool the vehicle, and in winter, I want to preheat it. Then we can ask the question, what really needs preconditioning? And for the electric vehicle, that would be the battery, mostly for functionality or lifespan, I should say. And of course, then also the passenger cabin, and that is really for reasons of comfort. If we look into typical statistics of how cars are being used and what kind of access to power sources they have, you see this here on the right side. We see that 2/3 of cars have access to electric power during night, and that a car is really, most of its lifetime is parked. That means that the concept of preconditioning makes a lot of sense and is feasible. When we talk about especially the battery preconditioning, we need to realize that the lithium-ion batteries especially are very temperature sensitive. The optimal temperature range, we already learned, is very close to the comfort zone of humans, somewhere around 20 to 30 degrees C. And if we go to either conditions that are either very much below or very much above, then we can either severely reduce the performance or even permanently damage the battery component. We also realize or experience that the temperature range for battery charging is even more narrow. So that needs to be taken into account when designing these charging systems. So why is the preconditioning so important? That is because the onboard installed capacity of the vapor compression system that Jürgen just talked about is generally limited. For conventional vehicle with internal combustion engine, I would put it somewhere around maybe 6 kilowatt of peak heating and cooling. and things change a lot if we go towards the electric vehicles. So the trends clearly there are towards much larger capacities. We're talking here now maybe somewhere between 15 to 20 kilowatts of cooling load. Why is that? The cabin conditioning is still pretty much the same as before, but in addition, we have now also what we already mentioned, the battery conditioning and the electronics cooling powertrain components of these high-powered electric components. What that also means is that as we're going to these larger and larger capacities, that operation in so-called part load efficiency becomes very important. This is why electric vehicle manufacturers mostly consider this type of scroll compressor you see here on the bottom, which is a machine which can be nicely speed controlled over a wide range without losing efficiency too much. Then the amount of electric energy that I can carry around in the vehicle is largely limited. We heard that in our first presentation. So we're talking at the moment about maybe somewhere to 50 to 100 kilowatt hours. And as we experience these more harsh ambient conditions, either on the high side or the low side, the driving range is reduced drastically. And that is for two reasons. First of all, the battery itself performs not to the optimum level as we experience these lower or higher ambient temperatures. And of course, I also need to spend energy on the thermal management system itself. So there's really these two reasons that limit my driving range. Let's first look at the preconditioning of the passenger cabin. As mentioned, that works both for heating and cooling, and we want to make good use of the connection to the power grid while we are plugged in. And so basically we use the air conditioning or heat pump components that are installed in the vehicle and power them while being plugged in. So in other words, we really want to reduce these very energy intensive vehicle warm-up and cool-down phases. We have here some typical capacities here for the cooling side, for the heating side, for the heat pump side, that we need in steady state operation. So you see at minus 20 degrees C, we go up to easily 5 kilowatt. And then of course, if we have a heat up curve or cool down curve, these numbers even increase more. Preconditioning of the passenger cabin works extremely well, especially for short drives. I can take advantage of thermal storage effects. In other words, the mass of the interior cabin components nicely store that either heating or cooling effect. And if the drive is not too long, my vapor compression system doesn't need to work too hard while I'm on that short drive. Another trend we see in electric vehicles is if we look towards autonomous driving, we can predict that the cabin load will increase for electronics cooling. So as there's more and more systems for safety, for the driving feature, but then also for entertainment. So the prediction is that the load in the cabin will increase, maybe quite substantially. And that means that the sensitivity also inside the passenger cabin will increase towards temperature change. So this is maybe a new control feature that nowadays in cabin comfort cooling, we don't see to that extent yet. If you look at the preconditioning of the EV battery, we first can take a quick look how these batteries are organized. First, we have the battery cells, which can take on various shapes. Here, these pouch designs or cylindrical designs, prismatic designs, whatever it is. And then we can package them into modules and then make many modules to come up with what we call here the pack. And we want to now use our active and heating and cooling concepts like the air conditioning system or the heat pump to achieve two things. First is to maintain the battery overall temperature in the range of 20 to 30 degrees Celsius, which is really the optimum or peak performance temperature range for the battery. But we also need to pay special attention to temperature uniformity. So that is equally important. It doesn't help us, if we chill the lower side, maybe the battery sits on some cold plate to very low temperatures, and then the upper side of the battery becomes dangerously hot. So what happens if I don't stay within these temperature ranges? If we go to very low temperatures, the chemistry of the battery becomes very sluggish. We can have this dendritic growth. And if we go the opposite end, if we go to very high temperatures, this is when these irreversible damages start to happen. We see here in that data graph here, the capacity retention. So if we continuously cycle the battery at a very high temperature. So we see as the number of cycles increase that the amount of capacity, or the number of capacity here, that the battery can retain is decreased. So this indicates that there's a permanent kind of damage effect. If you talk about battery charging and heat rejection, there's various levels of battery charging. These first two levels, they're called level 1 and 2. This is what you can do easily from your home, depending on whether you provide 120 volt AC in the US or 208. You see typical charging times. Now, where it becomes more interesting is when we talk about fast charging. So this is either level 3 or what we call next generation. This is when more high-powered power sources are involved with the attempt to cut the charging time, to well below under an hour. And for these extreme fast charging systems, we're talking maybe about 10 minutes to charge a 200-mile drive range. If we do normal driving in our electric vehicle, then we have on average maybe 3 to 4 kilowatt heat rejection from the battery. If we're talking about fast charging, that number increases many times over to maybe about 20 kilowatt of heat rejection. Again, showing that the amount of chilled fluid or cooling capacity that we need simply increases by several times over. If you look at the extreme fast chargers, the problem becomes even more pronounced. In this case, the current that flows through the charging cables gets so high that we need actively cooled charging cables. So it's not only the battery that wants to reject the heat, but we also need to reject the heat from the charging cables themselves. And you see there's one concept illustrated here where you have an additional channel to provide that coolant to keep the temperatures within acceptable temperature range. Then a quick overview of how to implement preconditioning. So I already mentioned that we want to use, of course, the infrastructure that we have installed in the vehicle. So the vapor compression system is ideally suited for this. The question is, do we use it externally powered or from the battery? Both is possible. If I'm connected to the grid, of course, I want to power externally. If you talk about heat source, Jürgen briefly touched on it. There is several ways of how to get energy into the heat pump. So one would be from the air that could lead to frosting issues on the outdoor heat exchangers. I can collect waste heat from the electronics or the battery. That all works nicely, but when the ambient temperatures become very low, of course, the amount of energy you can gain from those sources are limited. And there's also concepts where you use PTC to feed the heat pump in a strong thermodynamic sense. This is not a real heat pump anymore, but that may be a little bit besides the point here. One important aspect to consider is whether free cooling is available. That is, you may run in a situation where your ambient temperature is so low that you can readily reject heat to the ambient. So it would be good to harness that kind of temperature difference without having to run the vapor compression system. So then you can basically what we call free cooling. You just dump that battery heat to the ambient without having to drive the vapor compressor. There is several concepts here. The older air-cooled system where you have an evaporator, you're blowing cold air, not the most dynamic systems. And also there is a little bit of issues with uniformity, where we see most work being done here is on the liquid-cooled systems, where you have these battery chillers or new products that are really starting to appear to take care of the battery heat with circulating fluid through the battery. That can also be augmented then with a PTC heater just to heat the battery in winter. Another design that we see are these self-contained chiller modules. In that case, you can make the system very compact. You can maybe also use fluids that have a little bit more hazardous potential, like flammability or so forth, because the charges are much lower. In that case, you would also do the cabin conditioning with this chilled fluid. Another approach I want to briefly mention is refrigerant DX cooled. That is a little bit different than the battery chillers here. That is like a second evaporator, and you're directly expanding the refrigerant into this plate here, and then the battery rests on top of this cooled plate. Thereby you eliminate that second heat transfer loop, and things can become a little bit more efficient, but uniformities are a little bit more of an issue here. Then some of the future directions I briefly want to mention. We already heard a lot about refrigerant selection, so there's all kinds of considerations from performance to the cost of the fluid versus system, environmental and safety, and so forth. One thing they haven't talked much about is reliability. So now, after realizing that the system is needed not only for passenger comfort, but also for functionality of the battery, the importance of the AC or HVAC system is ever increasing now. If you compare typical car life, here is around 6,000 hours, which is a relatively small number if you compare, to household appliance, for example. But still, now that we have the additional functionality in winter because of the heat pump, the number of operational hours of the HVAC system increases. That also makes us consider the sensitivity to refrigerant leakage. Most of us either have had the problem or know somebody who had the problem with refrigerant leaking from a car. If that happens, of course, that has now different consequence if the functionality of the battery is affected. Another point we touched on is the limitation of capacity. So we know these trends are going towards the higher and higher capacities. So what can you do? Either you install larger components or you try to tweak and optimize what you have in existing size. For example, going to these compressors with higher and higher speeds, or come up with more improved battery cooling concepts like this direct contact evaporation, where some heat transfer fluid, volatile fluid, is surrounding the battery cells directly, thereby increasing the achievable heat flux. So there's all kinds of active work going on in this area. And this is my last slide here, just to sum up on the technology drivers. So we are after shorter charging times, increased efficiencies or reducing the losses, and of course, increasing the power densities. A lot of people are waiting for more and more breakthroughs in battery technology, which means hopefully there will be something with reduced heating and cooling demands. Maybe as an example, we could state the liquid-cooled PCs. There were many folks, 20 years ago, predicting that every laptop will have its own little air conditioning system. That never happened because, of course, electronics became more efficient. And maybe we see something similar in the future for the battery technology. Maybe a last point here for consideration is energy efficiency. If you think about switching to 100% renewable, the concerns in terms of energy cost or even emissions may now be of less concern. So that changes the playing field quite a bit. And also the possibility to link the electric vehicles to building systems. As we're generating more and more renewable energy from solar, this is what the utilities up here, what they call the duck curve. It basically shows the mismatch between when solar energy is produced versus when the energy demand is the highest. And so that kind of mismatch could nicely be buffered by the use of electric vehicles that are tied into the grid, which means we could charge them when the solar energy is available, and then discharge them a bit, to flatten out that so-called duck curve. And this is what I had prepared for you. And with that, I hand over to Jürgen Rettenbach.
So I try to get the screen.
Jürgen, we see your desktop, but not the presentation.
Do you see the presentation now?
Yes, now we see.
Now it is. Okay, perfect. Perfect. So my name is Jürgen Rettenbach. I had been working for Daimler for 40 years. And in my presentation, I will show you or talk about industrial trends. In my first slide, I will take you through the anchor points, starting with the generic term comfort.
Sorry, Jürgen, to interrupt. I think your monitors are also swapped. We see the presenter mode, not the full screen.
Okay, let me try to. I have to press here, I guess, and maybe this one, and hopefully it is done now. Better?
It's loading. We still see the presenter mode.
Okay. Okay. So can we go do this now in this way, or I do not see how I can make it.
Great. I think it's visible. We can continue. Just a heads up, we see your next slide too.
Okay, thank you very much for doing this. And I will take you through the anchor points, starting with the generic term comfort at the top of the picture and turn clockwise. I have to do the next slide. Okay, this one. Okay. For the auto industry, the development of a thermal management system comply all subjects of expected electric vehicle performance. The thermal management functionality is a decisive factor in terms of range, weight, and system cost, in addition to the e-drive. The comfort, heating and cooling system shall provide fast and permanently a comfortable climate in the compartment. This can be expected for a wide range of cabin types and spaces. The thermal system is essential for range-sensitive air conditioning and traction battery tamming. It has to be effectively operated between -35 to 55 C, as well under severe boundaries as solar radiation, high moisture, wind, rain, snowfall, etc. The cooldown of a solar-soaked compartment or a heat-up of a chilled cabin, to explain this is a time from switching on until getting comfortable cabin conditions, shall unfailingly be attainable. This comes along with users' expectation for technically warm or cold airflow spontaneously after switching on. Thermal interior comfort has, in the almost cases, the right of priority in AV. The TMS must provide for the vehicle interior sufficiently dried, draft-free, and properly distributed tempered air ventilation. Further, to avoid hazards to passengers and traffic, a clear view through the glazing is needed, what requires a defrost and free of fog conditions. The traction battery, as we heard already, shall be tempered, advantageously kept in a temperature window between 15 and 35. It is heated or cooled by a brine flow or directly tempered by a magnetic resistant heater, or cooled by the vent outflow from the compartment. Since range decline for EVs is critical, electric energy usage and thus a reduction in range due to interior comfort and traffic safety must be kept low. Therefore, from an energetic necessity, a high air recirculation rate is desirable. Furthermore, heat pump mode for using environmental or waste heat is beneficial and therefore a sound development trend for the latest vehicles. The desire for high comfort and enhanced functions often entails a complex system architecture. This causes a considerable number of mostly non-standardized components and fluid connectors, which leads to an elevated component production cost. The effort for OEM and their suppliers go into intelligent concepts and pre-mounted assemblies in order to master the complexity despite of an appreciated increase of functionality. From a cost perspective, it is always the trade-off between implied technology and cost boundaries. The total mass of an EV is a physical dilemma itself, due to the battery capacity versus the vehicle mass. Environmental aspects do not play an equal important role at all markets, while auto manufacturers claim CO2 neutral production for the entire vehicle. Refrigerants and energy consumption are something to be separately considered. An overall development target is high range associated with low energy consumption. The range decline at elevated or lower temperatures shall be low. To explore this, drive cycle tests with dynameters are established. Since the uploaded energy in the battery is determined after any test, the specific energy consumption for that cycle in the set environment can be calculated and comes out in kilowatt hours per 100 kilometers or so. Further, the range decline for summer and winter driving can be expressed and shows the impact of the thermal management system relative to normal temperature range. The capacitor requirement for the thermal management system, it is typical, and I draw on the y-axis we applied the thermal capacity for the vehicle cabin. On the x-axis, I draw the ambient temperature. Let's start with the heating capacity. For heating in chilled cabin, you need a higher thermal capacity than steady state conditions. The high heating capacity is shown here in red and dotted, then passes into stationary heating capacity applied to the red full line here. And values range from 6.5 kilowatt at -20 down to 0.2 kilowatt, which is a challenge for the compressor, with air mass flows from 30 grams per second to 110 grams per second. The heating capacities between about 5C and 40C are particularly problematic for the EV, as the air is often air conditioned and then electrically heated for comfortable blowout temperature. These operation points show an energetic advantage of the heat pump, as in the mode of cooling, sufficient heat is available due to compression and heat absorption. As an operator, the cooling capacity is similar. For cool down the cabin heated by the sun, you need a higher cooling capacity than for persistence. The high cooling capacity shown here in blue and dotted then passes into stationary cooling capacity applied as full blue line. Values range from 6 kilowatt at 40 degrees down to 0.4 kilowatt at an air mass flow between 30 grams and 150 grams. The ellipses are typical cooling capacity for fast charging at 35 degrees. They amount about 2.5 kilowatt for steady state conditions of the cabin and about 4 kilowatt for battery cooling. On this slide is a circuit application for thermal management system shown in principle. Trends for the architecture depend now on whether only an electric vehicle should be considered or an entire vehicle platform with a wide variety of powertrains, including EVs, considered. Here we show you 4 basic outlines, which from the left shows the thermal management system for an internal combustion engine vehicle, a circuit for a hybrid vehicle, and a circuit for a battery electric vehicle. The refrigeration circuit for the ICE is state-of-the-art and consists of a compressor, condenser with dryer receiver, expansion valve, and evaporator. A water heated heat exchanger, perhaps supported by a PTC, heats the air in winter. The circuit for the PHEV is very similar. It is also a parallel evaporator branch for the chiller for battery cooling. The circuit for the EV is quite the same, only a few components offer enhanced capacity. Thus, the chiller must be enabled for fast charging and the entire heating capacity must be provided by a PTC. The circuit for the EV heat pump looks to some degree similar, but the changes are obvious. It is another air or water side condenser or gas cooler arranged directly after the compressor for the heating usage, adjacent by a throttle level. The switch between AC to HP mode happens by selecting the throttle level before or after the condenser in the front of the vehicle. I come already to my last slide. I will start to explain the further needs at the bubble airy circ, most right of the picture, and turn clockwise. The HVAC regulates the air intake and outlet quantity for the vehicle interior as well as the humidity, so already tempered air is reused and reduces electric energy demand. Humidity sensor and temperature sensor is needed to control the circulation ratio. For an EV, it is obvious an individual driver cooling and heating system is mostly sufficient. This requires a left-right split up in the HVAC, including recirc air intake and separatory outlets. The defrost airflow is still needed for the entire windshield. Autonomous driving computers combined with more passenger entertainment equipment will lead to iconic component cooling. TMS will be toughened to provide this functionality. In operation modes with less but still sufficient comfort are proven for range enhancement. In this context, heated and cooled surfaces are given their task as secondary measures. Further strategies are in place to reduce thermal comfort but secure vehicle drivability in case of low battery charge. Conventional HVAC are spacious components. Development efforts are observed which reduce packaging volume and allow positioning outside the compartment. The standard AC components consist of a scroll type compressor, microtube air cycle heat exchanger, plate type coolant, refrigerant heat exchangers, expansion devices, switching valves control and steer the fluid flows. There is a pressure on the manufacturers to further optimize the components and group them together into assemblies. Interior air quality is improved due to customers' request. The package space is for combustion engines is open for the use of large filters. We talked about the refrigerant already from Jürgen. Under the sustainable idea, refrigerants are discussed. A large auto manufacturer is claiming that he introduces the world first heat pump using the natural and climate neutral refrigerant CO2. Due to the high efficiency, it is the most energy efficient way to heat an EV at cold outside temperatures. Others are requesting for a hermetic system the usage of flammable refrigerant at low quantities. Windshield heating is beneficial. Electric power demand is lower due to the reduced air mass flow through the cabin and extension of recirculation air. Glass roofs are a strong market demand, while vehicles with medium-sized cabins have sufficient cooling capacity even with large glass surface. There is an obvious deficiency in larger cabins. A trend towards low transmission factor glass is noticeable, and preconditioning, we have heard about it. It is a comfort feature with EV. Thanks for listening for today's last contribution, and I hand over to Eileen for the discussion.
Thank you, Jürgen, and thank you all the panelists for sharing their insight. We heard some very interesting topics today, covering from major challenges in EVs, the architectural, then deep dive into available refrigerants, cooling cycle, heating cycles, heat pumps, the preconditioning, and Jürgen's insight into current and future state of the industry. At this time, just also offering one round of virtual applause to our panel speakers and panelists. Thank you for sharing your insights. We have about 14 minutes for questions, and I can already see there are some very good questions. So let me dive into questions. Just also a reminder, you can still submit your questions by clicking on Q&A button at the bottom of the page. So first question, this is for you, Professor Ramon. Nicholas Robert Jankowski is asking, you mentioned the critical battery cooling events involve surge conditions, rapid charging, cell imbalance, and similar events. Can you comment on active and passive strategies to address thermal transients in the thermal management system rather than over-designing a simple system capacity to deal with such high transient events?
Mm-hmm. Interesting question. Depends what the circumstances are, but it's being considered, for instance, to use for transient event phase change materials or direct contact evaporation. So change in phase will absorb or release a large amount of heat in a relatively short time, and also that will enable the different cells in the pack to be subjected to the same rate of cooling. And Stefan mentioned a little bit about that. Now, if that is happening during the fast charging events at the charging stations, instead of over-designing the thermal management system in the EV, then the possibility is to utilize chilled coolant that is provided directly by the charging station. Stefan also mentioned the need to cool the cables for those large heating charges. But in addition to that, it could be some coolant going to help cool the battery during this transient charging event.
Thank you, Professor Ramon. The second question is for Jürgen, Professor Kohler. The question is, it's from one of our anonymous attendees. In one of your diagrams, you show that receiver is on the lower pressure side of the circuit. This is an accumulator for the refrigerant. Is that a required location in a heat pump application, or could it be placed on the high side, i.e. on the coolant liquid side?
It depends. For a refrigerant which condenses, you can also place it on the high pressure side at the outlet of the condenser. However, if you use CO2 as refrigerant, you have a transcritical cycle, which means you do not have a phase change at high pressure level. And then it's better to store the amount of mass at the low pressure side at the exit of the evaporator, because you have a liquid level which can go up and down. So you can store as much mass as you want just by changing the liquid level. But you only have a liquid level at the low pressure side, so phase equilibrium between liquid and vapor. You don't have it at the high pressure side for a transcritical cycle.
Thank you. That was an interesting question. I'm trying to. There was a question for Stefan. Stefan Parcelbel, you mentioned that this is a question asked for Subonic. The question they ask is, you mentioned that battery should always be kept within -10 to 60 degrees Celsius or similar range. Is that a requirement for when battery is in operation, or is it a storage requirement as well?
Okay, thank you for the question. Yes, and I apologize if I was not overly clear on that. Of course, the temperature at which you can store the battery when the vehicle is not in use, is larger than when the vehicle is in use. So you can go down to more extreme temperatures, -20, -30, and let the battery just sit there without using. But the moment you want to use the vehicle, it's strongly advised, of course, to precondition and to heat it up to avoid those irreversible damages. I hope that addresses the question.
Thank you. And also the question for Jürgen Wertenbach. You covered some of the major trends in EVs and some future trends. If we go towards shared economy, that vehicles will be shared between different people, so the number of hours that vehicle will be in use will go from 2 to 3 hours average that we have today to maybe 12, 20 hours per day. Do you expect a change in the way that we look at thermal management of vehicles?
The vehicle is today already designed for much more hours than an ICE vehicle. This is already implied in this strategy. So we're talking about numbers above 10,000. That's all.
And in terms of architecture, do we expect a architectural requirement change in the architectural, or the same architecture will be?
I would say, if the boundaries are the same as today, for example, with the heat rejection in the front end, with the compartment need of capacity, the architecture will not change too much. There might be other effects or other solutions possible for heat rejection, but I think this is still in the research phase.
So, thank you.
Mm-hmm.
There are some questions for the panel. So let me put one from Geslio Lopez. They ask, what is more efficient for cooling the battery? Is it the parallel flow or having cold plates at the bottom of the pack?
I can maybe start with some thought I have about this. First of all, how do you define efficiency here? To make sure the battery life, is extended as long as possible, or are you looking from purely thermodynamic efficiency point? If it would be the latter, then from thermodynamic point, it is much better to cool as close to the temperature that you want to absorb from. And if you look into the thermal resistances that you experience, so it is very often the contact resistance between whatever fluid and the battery cell itself, which poses the majority of the resistance. So if you can improve that resistance, then the efficiency goes up. This is why we see, for example, these direct contact evaporation concepts popping up. As for the cold plate underneath, you can, of course, condition to whatever low temperature you want and can get rid of all of the heat you need. I would be more concerned there with temperature non-uniformity. So if you make that cold plate too cold and the battery pack has, extended height, it is very difficult to guarantee that very narrow temperature range to keep the cells in. And so those are my few cents. I don't know if somebody else wants to chip in.
I guess, any other input from the panel?
No, I could agree. Certainly, the cell to keep the temperature uniform, not only within each cell, but also across the thousands of cells. Some are connected in series in parallel. Because it then degrades much faster than the others, depending how it are connected, that will degrade and affect the whole battery lifespan, but also the efficiency during operation or the performance. So really there are interesting thermal challenges these days for these, at least the current chemistries of lithium-ion batteries. Good to be a thermal engineer, I could say.
There's not only thermodynamics, which govern the design of such battery cooling, but also the cost, which is a surprise that costs sometimes govern the whole design. And we investigated that and found that there is a certain optimum if you use cold plates parallel to the prismatic cells. And you put 2 cells and then a cold plate, and then you put another 2 cells and so on. That looked under certain conditions as a very efficient way, which can be also doable regarding the costs to get a very homogeneous temperature distribution and efficient cooling with a reasonable cost.
Yeah, perhaps speaking also about cost, another important issue is how we keep the batteries such that they have an effective second life. Because currently, after the capacity of the battery reduces to 80%, it is discarded. So there is an economic factor later on for the second life, and also there is an environmental factor, how we're going to keep these millions of batteries that will be disposed. So the opportunity really to repurpose them, particularly for storage of energy, and that storage of energy could be for renewable, but also could be for recharging batteries. We know that DC to DC recharging is more effective than charging directly from the grid. So there are a number of interconnected factors there that also affect many of the decisions being made.
Interesting. And Jürgen, you mentioned cost. There's one question from anonymous attendees that, do we have any estimate of what is the cost of thermal management system in the overall pack cost that you shared?
It's a good question. I do not know these figures, honestly, because I do not know the costs from all the other components. I know the cost from thermal management system, yes, but I do not know the other costs.
I can provide rough estimates from what is in the literature. The current cost of the battery lithium-ion with the thermal management and the packaging right now is of the order of $150 per kilowatt hours, whereas the cost of the cells themselves is of the order of 100. So really seems that extrapolating from these numbers, about 50% is the increase of cost, kilowatt hours, when we go from the cells to the battery pack, including the thermal management system. So that means that 1/3 of the 150 seems to be the thermal management system cost plus packaging. So that gives a rough estimate, but certainly industry, I'm sure, has those numbers or those, calculated.
Okay. Thank you all. It's a great discussion. I think we are at the end of our time. So at this point, I would like to share slides for our conclude this panel at this point. Thank you again. Another round of virtual applause for the panelists. Thank you for answering the question. Very good question. Thanks for participants. Please send us any suggestion that you have for future topics, presenters, and format of this panel. We would appreciate that. With that, I will pass it to John to talk about our future sessions.
Thank you, Aiden. Thank you, all the panelists. I have just 3 brief slides, so everybody hang on, don't sign off just yet. We have our next webinar on September 2nd will be about the Earth's energy balance, which is arguably the single most important heat transfer problem that there is. For this panel, we have a number of the world's leading atmospheric scientists who will discuss the data and the models and the physical phenomena that govern the temperature of our planet and how it may be changing. We'll hear about atmospheric aerosols, the role of oceans in storage, greenhouse gases, and other factors. So please do attend for this one. Next slide, please. Following that, on September 15th, we will have a panel on personal thermal comfort, how you can manage temperature at the level of an individual person. Temperature and I suppose moisture. This will also be an exciting event. Please do put that one on your calendar as well. And then finally, the last slide, if I may. We would like your suggestions for future panels. Please just type them into the Q&A box. We'll record these. You can sign up for our mailing list by going to the link at innotherm.mit.edu. And that website also has our videos of past panels. We'll have the video of this panel, and it will also have Q&A. So thank you all for attending. I look forward to seeing you on September 2nd.